Okay, we're going to go ahead and get started with Chapter 7. I appreciate you all being flexible with the recording being posted online. I know that some students are very concerned. It seems that the UHPD has investigated the individual, or at least the postings, and has concluded that there's no immediate threat or harm that is potentially going to be imposed on students at UH. So I think everything is fine. I will be at the university later on today if anybody has questions and we can meet. I'll also be available tomorrow. Please send me an email if anything is unclear or you're having a difficult time understanding any of the material. So Chapter 7, although it may seem very new and different, I hope by the end of this lecture you recognize that it really parallels what we did in chapters 5 and in chapters 6. And so all we're doing is taking that information and then applying it to sample means instead of individual scores. And so we'll go over all of this, and hopefully, as I mentioned, by the end of the lecture you'll have a better understanding for this. The one consideration is using standard error instead of standard deviation. We'll talk about that. But again, if you have any questions, please feel free to email me or set up a meeting with me. Remember that everybody can use a 3x5 white index card during the test on Thursday. Everybody's only allowed one. Feel free to write on the front and back if you've had a particularly hard time with understanding a certain example. I would encourage you to maybe include that example on your card so that you can reference it during the test. Yeah, just remember to bring your Scantron, pencil, stuff like that. Your TA and I will both be there. And yes. Okay, so let's go ahead and get started. Okay, so for Chapter 7, what we're really going to do is focus on distribution of sample means, describing the distribution by shape, expected value, and standard error. We're going to go over exactly what that means. We'll also describe the location of sample means by their z-score and determine probability corresponding to sample means using z-scores and the unit normal table. So if you were to take out sampling means or any type of, sampling means, and just replace it with a sample of scores or a score, you know how to do that. And so all of that knowledge is going to be really important with this lecture because you're going to be doing that to these data as well, except in these instances we're using sampled means. We're not using individual scores. Okay, so as I mentioned, things you'll need to know, random sampling, which we're going to go over again, probability and the normal distribution, so determining the probability of obtaining a score if a population is normal, which we've talked about, and that's going to be very important for this chapter, so it's really necessary that you know that. That's why we spent so much time on it. I hope that you have a good grasp of it. Touch base with me if you don't. Z-scores, so being able to compute a z-score that describes exactly where the score is located in the distribution, which in turn is necessary for you to understand probability of obtaining a certain score. Those things are going to be paramount with this chapter because we're moving into this realm of sampling means and how we know where a sampling mean falls on the distribution and what's the probability of obtaining a certain sample mean. Okay, so the location of a score in a sample or in a population can be represented with a z-score. We have gone over this, we've done it. You guys should be very familiar with, if I give you an x and a mean and a standard deviation of a population, I say, what's the z-score? You know how to find that. So thus far we have focused on a single score as in the example I just provided. But most studies involve much larger samples. It's not just a single score. The N is not 1. And so researchers typically want to study entire samples rather than single scores. so that we can answer questions about probability of sample means. So when we focus on one particular score, we kind of we don't really understand much about the actual population, because if it's just one score in and of itself, it's going to, potentially have bias. It's going to be different than other single samples that we could have we could have drawn, things like that. So basically, a way to get around that is to draw larger samples. So N of 30, N of 100, things like that, and then extrapolate the information we learned from that to our population. So tests involve transforming a sample mean to a z-score. The way that we transform a sample mean to a z-score is identical to how we transformed a single score to a z-score. The only difference is that instead of having a single score minus the population mean, we have the sample mean minus the population mean, and we're dividing by the standard error instead of the standard deviation. So this all should become very clear as we continue through the chapter. So lots of samples of a particular N can be derived from a population, and that will be very important as we discuss expected values of N, M, and things like that. So samples provide an estimate of a population. They're not as reliable as if we had all of the information from the population, and that is why we have standard error. Okay, prior to getting to standard error, which is a metric to assess sampling error, let's talk about what sampling error is. This is more of a conceptual piece. This is not error that indicates that a mistake was made or anything like that. Sampling error is just a natural discrepancy or amount of error between a sample statistic and its corresponding population parameter. And so we saw this in whenever we were looking at standard deviation in populations and individual scores. There's a natural error or discrepancy between the score and the mean, the population mean. And so in instances when we are focusing on distributions of means, which is what this chapter focuses on, distribution of means, not distribution of individual scores, we call that sampling error. So that is the natural discrepancy between a sample statistic, such as a mean, and its corresponding population parameter. Samples are variable. Two samples are very, very rarely identical. How might they differ? I mean, they will have different people in them. They could have different number of people. People carry a lot of characteristics with them that just make them unique. For this reason, when we use a sample, most likely, if we pull another sample, they're going to be different. If they come from the same population, then we can use that information to infer information about the population, but it doesn't necessarily mean that the two samples are exactly the same. So the question comes, if samples and populations are so different, how can we establish a simple rule for their relationship? Well, a lot of people have devoted their times and their time in life to figuring this out, and so we can just kind of learn about it. And part of understanding that is the distribution of sample means. So the distribution of sample means have certain characteristics that are common across all of the distribution of sample means. We're going to go into those in a second, but to just get us started, this comes back to the idea that samples do differ from one another. So given a random sample, it is unlikely that a sample means will always be the same. That's highly unlikely. I would say if you were to think about it in terms of probability, it's just never going to happen, right? The distribution of sample means is a collection of sample means for all possible random samples of a particular size that can be obtained from a population. So if you think back, I can't remember exactly which chapter it was in, whenever we were discussing, we have data, our population consists of data from 10 people. How many combinations of N of 2 can we have? And so we worked through that, and this is, I think it was chapter 3, maybe 4, whenever we were talking about bias and unbiased sampling and bias and unbiased statistics. And that's what this gets into. And so if you have a population and you have a particular N, and then taking all of the random samples of that particular N, and you are to graph them, and you are to set them up in some type of distribution table or distribution graph, that's what the distribution of sample means is. The distribution of all the random samples of a particular N that can be obtained from a population. We can use this to predict sampling characteristics. So the probability of selecting a sample mean is the same as when we were talking about the probability of selecting a particular score. And so, for instance, whenever we had scores, say we had 100 scores, they were all different. It went from like 1 to 100. What is the probability of selecting a 5? Well, the probability is 1 out of 100, because we know that the formula for probability is the occurrence over the number of possible outcomes. The same holds true for distribution of sample means. Essentially, if we have 100 sample means ranging from, let's do 1 to 100 again, what is the probability of us selecting, and everyone is unique, okay? What is the probability of us selecting a sample mean that has a sample with a mean of 25? If everyone is unique, the probability of that occurring would be 1 out of 100. So the same principles still apply here. What we're doing is we're moving from X values, single scores, to sample means. The reason why we're doing this is because when we do research, we're not particularly interested in an individual's characteristics as we are in an average across a group, a sample of people. Okay, so the sampling distribution. As I've mentioned, the distribution in earlier chapters were distributions of scores from a sample, so single scores. The sampling distribution is a distribution of statistics, not scores. And so when we're speaking about a distribution in particular, like just saying distribution, that's going to be of scores. A sampling distribution is going to be of a statistic, of typically a mean. And the reason why is because this is capturing the statistics from several different samples. It's not an individual score per se. So that's why we're calling it a sampling distribution. So the distribution of sample means is a special kind of population. And what that basically means is that if you were to resample over and over and over and over again, what does that look like? That is a unique population that we can infer information about. The distribution of sample means is obtained by selecting all the possible samples of a specific size N from a population. We've already talked about that. I went over that in this slide. Right here, this is the same information. I'm just trying to present it in different ways. So the distribution of sample means is obtained by selecting all the possible samples of a specific size from a population. You have a population, you take N of 30 and you sample it, you see what the mean is, and then you put it on your distribution table or your distribution graph, and then you sample the next one, N of 30, you do that again, N of 30, do it again, do it again, do it again. Essentially what it comes down to is this is a distribution of means. A sampling distribution is a distribution of a statistic, and when we're doing this for sample means, this is a distribution of means. So how do you make one? Exactly like I just went over. You select a random sample of a specific size from the population. So let's go with 30. You calculate the mean. You place the mean in a frequency distribution. You select another random sample with the same number of scores, n of 30. You calculate the mean. You place the mean in a frequency distribution, in the same frequency distribution that you place this initial mean. You repeat until all possible random samples with the same number of scores have been plotted. After doing that, you will have made your sampling distribution. So as I mentioned, there are important characteristics of distributions of sampling means. These are things you just really gotta memorize these things. These are very important considerations, and I think that they make it better, they make it easier to understand why exactly we are using distributions of sample means versus distributions of individual scores. So the first thing is the sample means pile up around the population mean.